Hello everyone, it was my great pleasure to introduce our today's speaker, Simon Du from Computer Science Department. Simon got his PhD from Carnegie Mellon University in I think machine learning department, and working on a lot of very exciting topics from on our like computational aspects and reinforcement learning. And then after graduation, he moved to Institute of Advanced Study at Princeton and do a postdoc for 1 year. And he just joined the UWA this summer. And today we are going to hear his very exciting talk about reinforcement learning and some large state space.
Thanks for the introduction. Today I'm going to talk about some of my recent work on reinforcement learning, which with large state space and long horizon. I don't know whether like audience are familiar with reinforcement learning. So if there's anything you feel like confused about, please just interrupt me, and I'm happy to clarify about it. And if you have any question, please interrupt me as well. So these are the joint work with Jiang, so from like both departments, and Wilson Wang from Carnegie Mellon University. He's fourth year PhD student there, and Lin Yang from UCLA. Okay, so we all know that reinforcement learning is very popular and powerful in solving many real-world problems like robotics. This like dialogue system, some treatment effect problem, some education problems, some operation research problem, and more recently it's very hot in solving different kind of games like video games and the game of Go. So here, let me describe the setting first. So often we work in this Markov decision process. So basically, at each iteration or at each time step, we are controlling an agent, okay, which is at some state. Basically, a state describes what the agent can observe, can see, and the situation or the scenario the agent is at, okay? And then the agent will choose some action, which we call AT. So the agent chooses the action according to some policy, which is going to think of mathematically is to think of as a mapping from the state space to an action space. So the big S here denotes the state space, and big A here denotes the action space. And then the environment will receive the state and action, and will transit the agent to the next state according to some transition function P, which depends on both state and action. Okay. Also, the environment will give the agent some reward according to some reward function, which we call R. And the whole process, this will repeat for H times. Okay, so H is called the planning horizon because you will need to plan your agent in order to maximize your reward. So it's a long-term planning problem. So here, the goal here of the agent is to maximize the total expected reward. Where the first state is, let's say, a sample from some fixed distribution mu. And the goal here is to find a policy, which is again, a mapping from state to action space that can maximize its expected total rewards. Okay, so this is the standard Markov decision process. I hope everything is clear. So I would like to mention a special case of the Markov decision process, which is called contextual bandits. So this is basically a special case of Markov decision process with planning horizon being 1. Okay. So in this setting, it's very simple. Just each episode or each iteration, the environment will generate some state S1 from this distribution mu. And the agent will choose some action A1, and then you get some reward according to the reward function. So there's no long time like planning in the contextual bandits. The agent can just choose the the action that can maximize its reward. On the other hand, for Markov decision process, the agent not only need to maximize the current reward, you also need to consider the long-term reward, because you may transit to some state that can have larger reward in the future, but not very large reward at the current state. So that's called the long-term planning problem. Okay, so the main difference between these two settings is that there's no transition in contextual boundaries and there's no planning horizon like this H. Okay. So I hope this is clear. So the simplest or probably the most fundamental setting in reinforcement learning is called the tabular reinforcement learning. This is the simplest mathematical model to discuss about the properties of different reinforcement learning algorithms and problems. So the setting is like this. So we assume the number of states is finite, and our theoretical bound, like symbol complexity or computation complexity bound, will depend on the number of states. Also, we assume the number of actions is bounded, is also finite. And then we need to put some regularity condition on the reward. The rewards, like we say, is often positive or non-negative, and the sum of them is bounded by 1. Okay. So you can see here, we don't put any assumption on the transition matrix. So there's a long line of work analyzing the sample complexity of this tabular reinforcement learning setting, dating back to Kearns and Singh in 1998, where they designed some algorithm with sample complexity, which is here we measure sample complexity in terms of number of episodes, to show that polynomial number of episodes in terms of number of states, number of actions, planning horizon, and 1 over epsilon, you can find an epsilon optimal policy that is close to the best policy with this number of episodes. And there's later many follow-up works to improve this bound. So there's some, here are some representative works, for example, like Joshua and our show that you can have this kind of bound. And later in 2017, Agarwal et al. Show that you can have SA plus H or epsilon squared, plus some polynomial of SAH or epsilon to find an epsilon optimal policy. And there's some recent work in last year. They show that actually you can improve the dependence, the term that scales with 1 over epsilon squared to SA or epsilon squared, plus some polynomial of SAH or epsilon. However, so these are all the upper bounds. However, if you look at lower bound, it's actually only assume the contextual bandits lower bound, which is just SA or epsilon squared. So here there are 2 questions that people want to answer. So first, it's a problem that in many real-world problems, the number of states, the state space is very large. Okay, so we don't want to have our sample complexity bound that directly depends on the number of states. And secondly, it's more theoretical that you can see here the lower bound has nothing to do with H, but all the upper bound has a polynomial dependency on the planning horizon H. So we don't know whether this polynomial dependency is really necessary or not. Although this in the state-of-the-art bounds, this H only appears in the term that scales with 1 over epsilon in terms of instead of 1 over epsilon squared. So if your epsilon is very, very small, then basically you can show this matches lower bound. However, in the larger epsilon regime, this polynomial dependency on SA and H matters. Okay, so these are the 2 questions we want to discuss today. Is there any question?
Questions about what do you mean by the episodes on the current slides?
Okay, so the episode here means so here we will repeat these games for say number of episodes. So each episode you have H steps. So for each episode you play this environment for H times according to this oracle with planning horizon being H, and then you restart from the first state and play for H steps, and then you restart. So number of times, number of restarts is the number of episodes. So this is called episodic finite horizon Markov decision process, to be precise. I hope this is clear. Okay. All right. So let me expand these two problems a little bit more. So in many real world problems, for example, the game of Go or this video games, number of states is very, very large. Okay, like this number of large. So in practice, people have developed more advanced algorithms like deep Q-learning or combined with deep learning methods to solve these problems. But theoretically, we don't have a good understanding yet to understand how when combined with deep learning or other function approximation schemes, why they can solve these problems, and what are the sample complexity. So this is about the first problem. The second problem is actually formalized as an open problem in COLT, Conference of Learning Theory, in 2018 by Jiang and Agarwal. So they ask the following question. Let's say your number of states in action are just constant. Then can you show a h to the alpha, like polynomial number of planning horizon lower bound for some alpha bigger than 0? So why they have this conjecture? So all the state-of-the-art sample complexity upper bound scales is polynomially with the planning horizon h, although the lower bounds does not have this term. And more conceptually, like people often believe reinforcement learning is more difficult than contextual bandits because you need to plan in the long horizon. Okay. So because people believe reinforcement learning is fundamentally harder, so you should believe there's actually some lower bound that can separate these two. Okay, so that's in their open problem stated about why they believe there's an lower bound. However, today I'll show you this lower bound is not true. Like we will refute this conjecture. Okay, so let's begin from the first problem about large state space. Right. So yeah, so we're working in the setting where the number of states is very, very large. So when the number of states are very large, this is not a very new problem in machine learning. So let me remind you what we do with this scenario in the supervised learning setting. So let's say you want to build some image classifier for classifying images. So you can think of each image as a state. So to build this image classifier, of course, we will not use all possible images, all possible states around the world. Instead, we'll use function approximation to find a good classifier, to represent this classifier. So the key here is to restrict our classifier within some function class. For example, you can use linear functions, kernels, or deep neural networks. Okay. And theoretically, actually, we have a very good framework to understand the sample complexity of supervised learning. Basically, with d or epsilon square samples, we can learn an epsilon optimal predictor or classifier just by solving an empirical risk minimization problem. Okay, so d here represents a complex measure of the function class that you want to represent your classifier. For example, for a linear function, d is essentially the dimension of your feature. Okay, so you can use empirical process theory or pack learning framework to have this bound. Okay, this is a classical result in statistics. So this is for supervised learning. For reinforcement learning, of course, we can also use function approximation to represent something. But here is not very direct as the supervised learning setting because it's not clear what to represent using this function approximation. So the input of this function is often a state and action pair. But there are several things you can represent using the function approximation. The first is called Q-learni, which you may have heard about. I'll introduce that more in the later slides. So that's also called volume-based learning. Another class of methods called policy-based learning. Basically, you want to use your function to represent the optimal policy. Okay, so you restrict your optimal policy within some function class. And lastly, it's about model-based learning. Basically, you want to represent your models, which is the transition function P and the reward function R within your function class. Okay, so after you learn this transition P and this reward R, you can it can induce the output policy from this transition function P and reward function R. Okay, so these are the three main methods used in practice to use function approximation to deal with this large state space problem. Okay, up to now, are there any questions?
Yeah, I think I don't see questions, so maybe you can move forward.
Cool. So today I'll mostly focus on the Q-learning and the policy-based learning. So here, let me give you a setup about what is Q-learning. So Q-learning is based on the concept of Q function. So this is the definition of the Q function. So Q function depends on a fixed policy pi. So you have a policy. Okay, remember policy is mapping from the state to action. And for at each level can have a different Q function. So small h denotes the time step you are currently at. So the Q function defined as the expected total reward starting from the state S, and you take action A, then you follow the policy pi. So this is and then you take expectation over the transition and the reward. So the expected reward from the state and action A, and then you take the policy pi. Okay, so this is the Q function. So why Q functions are useful? Because suppose you know the Q function for the outcome policy. So let's say it's called Q pi star, or Q star for short. Then this Q function actually directly induces the outcome policy. Basically, the outcome policy is just a greedy policy with respect to this Q star function. At every state S, the outcome policy is just the action that maximizes Q star as a this Q function. Okay, so this is very easy to see. So in terms of learning, the Q function has a very nice property. It's this perturbation lemma. Basically, suppose you have an estimation of the optimal Q function, say at every level H, at every state action pair. So your estimated Q function is close to the optimal Q function within epsilon arrow. And then you choose your policy according to your estimated Q function, say this argmax A or all the actions that maximize your estimated Q function. Then this policy is actually a near optimum one. That is the expected total rewards of your policy, which I denote as this V function. Okay, this V pi hat. It's close to the optimal policy expected total reward within H epsilon arrow. Okay, so this basically shows that as long as you have good estimation of your Q function, and then you choose the policy that maximizes estimated Q function, then this policy is a very good one. Okay. Okay, so now let's discuss what's Q-learning with function approximation. So for Q-learning with function approximation, including say deep Q-learning as a special case, basically we restrict the function within some function class, which I denote as big F, so that there exists one function that can approximately represent the optimal Q function, Q star. So let me give you a very specific example. Let's consider this linear functions, or linear function class. So in this setting, we have a d-dimensional feature vector, say phi SA. So this is given to you. This feature vector maps a given state and action to a d-dimensional feature space. And so what do I mean by you can approximately represent the optimal Q function by a linear function? We mean that there exists some unknown linear coefficients, say W star, such that for any state action pair, this double star, the inner product between double star and this feature vector is close to the optimal Q function within, say, delta arrow. Okay, so when delta is 0, it's called a realizable case, and if delta is bigger than 0 but very small, we can often call it agnostic case or misspecified case. Okay, so the question I want to answer is that so given this assumption, can we find a near optimal policy with polynomial number of samples? So here, polynomial is in terms of the feature dimension or some complex measure of your function class and number of actions, planning horizon h, and 1 over epsilon. Okay. So remember, if we consider the supervised learning setting, basically this is trying to learn a linear classifier, or this is just a linear regression problem. And we know that with polynomial number of samples, we can learn a good linear predictor. But for reinforcement learning, we don't know whether we can do it. Okay, so this is the question we want to answer. So is there any question about the setting? All right, so here's our main result. So unfortunately, we give a negative result to this question. We can show that. So suppose you have a d-dimensional feature vector phi, and this feature vector is relatively high dimension. That is, d is bigger than, say, h over delta squared, where delta represents, remember, it's the approximation error. Okay. But even you have this assumption, you can say delta is very small, but as long as d is very small as well, very large as well, then we can show that there exists a class of reinforcement learning problems such that even finding, say, a constant near optimal policy, say 0.25 near optimal policy, you need exponential number of samples. So exponential is here is a to the h. A is number of actions and h is the planning horizon. Okay. So basically, we can show that in the agnostic case or misspecified case, and if your dimension is relatively large, you need to pay this exponential number of samples. But instead, in supervised learning, you don't need to pay exponential number of samples. You have d over epsilon square bound for this case. So a couple of remarks. So here, this is already a very strong assumption because we assume for linear function, you can use a linear function to represent the optimal Q function. So it also holds for more stronger function classes like kernels or neural networks because they are superclasses of linear functions. So this lower bound still holds for superclasses. Also, our lower bound actually holds for deterministic transition and the deterministic reward. So we don't introduce any stochasticity here. Even for this deterministic system, you need to pay exponential number of samples. Another remark that we can also further extend this lower bound to a stronger assumption case that for all policy, that there exists a linear coefficient that can represent this Q value. Okay. So even in this stronger assumption case, you still need to suffer exponential number of sample lower bound. Okay, so this is pretty bad. So first, let me give you a high-level idea why you need to pay like exponential number of samples. So let's consider a simple case that's number of actions 2, and we study this binary tree. This is a very classical scenario in the first algorithm data structure course. So here is this environment, it's a binary tree, and it has one reward on one of the leaf, but you don't know where this leaf is. Okay, so you can see here the number of states are very large. Like you have 2 to the h leaves, so you have 2 to the h states. So to find this, so the optimum policy is just this path to going to the leaf that basis reward 1. But to find this optimal path for this environment, you need to pay 2 to the h number of episodes. because you have no information about the other leaves. So basically, you need to try every possible path to find this optimal one. Okay. So remember, our goal is to construct, for this lower bound, is to construct a feature vector phi and some linear coefficient double star such that it can represent the Q function, optimal Q function approximately for every state action pair. So the main idea of the proof is the following for this construction. So first, we will use a one-hot encoding to represent this environment. Basically, we can say, like say feature vector, say psi, which is a very high dimensional feature vector. It's a scale with the state action, number of states and number of actions, and some linear coefficient W tilde, which has the same dimension. So, so these two vectors, whose the only non-zero entry of these two vectors corresponds to the optimal state action pair that on this optimal path. Okay, so basically, so if this state has reward 1 or its Q function is reward 1, then we then the entry of the psi and the tilde is 1, and for the other states, the entry is 0. Okay. So, but now here, this dimension of the psi and W tilde is very large, but we want a low dimensional representation that scale with d or h or delta square. So how do we do it? How do we construct the feature with relatively low dimension? So here we can use Johnson-Linus-Strauss lemma to compress the originally high dimensional feature vector to a low dimensional one with some approximation error. So basically, this lemma can compress a very high dimensional vector to a low dimensional vector and can preserve the inner products. Okay, so basically we apply JL lemma to psi and tilde and obtain phi and double star. So this is a high level proof. Okay, so this is for Q-learning. Another very important setting is called policy learning with function approximation. So here, this is the setting. So basically here we can, the function maps in state and action to say a real number. And the assumption is that there exists one function within the function class such that the optimal policy at every state S has this form. That is the action that can maximize this function value. Again, let's consider the linear function case. You are given the feature vector phi, and there's an unknown linear coefficient vector, say theta star, such that optimal policy has this inner product form. It's an action that can maximize this inner product. So this form includes many popular algorithms. If you're familiar or heard about this, deep reinforcement learning literature, there are policy gradient, TRPO, PPO, etc. So the question here is that can we find a near optimal policy with polynomial number of samples? Here again, polynomial is in terms of this number of dimension, the input dimension, the number of action, depending horizon, and L1 or epsilon, instead of dependency on the number of states. So for this setting, again, we can show exponential lower bound. Okay, so here we don't even need any approximation error. So even in the realizable case, that is, the optimal policy can be represented by a linear function of this form. Then there exists a class of reinforcement problems such that obtaining, say, constant optimal policy, you need a to the h or a to the d number of samples. Okay, so even for the realizable case, you need to pay exponential number of samples. So a couple of comments. Again, this also holds for kernels and neural networks, it's stronger function classes, and holds for deterministic transition and rewards environments. It also holds for, say, linear classifier. You can think of this function as a linear classifier because you are choosing the maximum value, which is you can think of it classifying the different actions. So even if this linear classifier has a margin, you still need to pay exponential number of samples. Whereas in supervised learning, sometimes the margin can give you some exponential improvements. All right, so in terms of proof, the hard instance is the same. It's a binary tree. Finding the optimal path, you need 2 to the h samples. But here we can embed to construct the feature vector and the coefficient using an epsilon net on the unit sphere. So we can assign one element from the epsilon net to each state and action pair. And basically, you need to find a specific component in the epsilon net. So, but the number of elements in epsilon net is exponential. So you need to pay exponential number of samples. That's the high-level idea of the proof. Okay, so I have given you 2 exponential lower bounds. So you may wonder when is actually like this reinforced learning with function approximation is actually solvable. You have some polynomial upper bounds. So here are some existing upper bounds. The first class of upper bounds put assumption on the environment. That is, you assume your transition function and reward function belong to some function class. Like, say, if you have a deterministic system and you have the first one is that you need to have deterministic system and you have approximation error goes to 0, then you can have a polynomial upper bound. And secondly, if you have a small number of hidden states, that you assume your observable states are generated according to some smaller number of hidden states, then you can have some polynomial upper bounds. It depends on the number of hidden states. There are some other upper bounds, like say Bellman rank, Bayesian rank, to characterize the complexity of the environment. And there's some recent work on linear MDPs, basically assume that the transition function belongs to a linear function class. There's another class of assumptions. It's called completeness assumption. So basically, it's a little bit weird assumption. It assumes that, say, your Q function is in some function class, and after the Bellman operator is still a linear function. So Bellman operator is that you apply your transition matrix or transition function on your function. So this is an operator, and plus the reward function. So after this operation, this function is still belongs to the, say, linear function class. So this assumption really comes from the proof. And then if you have this assumption, you can have some unbiased estimate of your current policy. This, high level why people assume this. And this applies to, say, linear function and some generalization of linear function called root dimension. So I would like to say there's still a very long way to go to understand when you can have a polynomial upper bound of reinforced learning with function approximation. And this is actually a very hot topic recently. And there's a workshop at Simon's Institute this year focusing on this kind of problems. I would also say some interesting separations. So if you compare with reinforced learning and supervised learning, we know that even for agnostic case, you can use ERM to find a near optimal policy, let's say classifier or predictor with polynomial number of samples. But for reinforced learning, you need to pay exponential number of samples. And secondly, there's a separation between module-based learning and policy-based learning, because we know that if you have no approximation error and if your transition and reward are deterministic, there is a polynomial upper bound, Ban-Wen and Wen-Rui. But on the other hand, we have an exponential lower bound for the policy case, even in the realizable case in this deterministic system. So there's a exponential separation between the module-based learning or the Q-learning and the policy-based learning. Another separation is about agnostic case and the realizable case. Again, we can consider the upper bound of realizable case of Q-learning in the deterministic system, where we have a polynomial upper bound, but we also have an exponential lower bound for Q-learning in the deterministic system. And here, for agnostic case, we need exponential number of samples. So there's another exponential separation between a good feature for linear function with zero approximation error, and good but not perfect feature. With so you have some feature, but they can only approximately represent the Q star function. And for those who are familiar with reinforcement learning, there's another class of setting called imitation learning. Basically, you can have some expert to tell you which action is the best action. It's like a subclass of policy-based reinforcement learning. And for that, you have an exponential, for imitation learning, you have a polynomial upper bound, even in the setting I described today. So there's an exponential separation between the imitation learning and policy-based learning, policy-based reinforcement.
Simon, I think there was a question in the Q&A about like on slide 20, I think probably previous slide. Does the P parentheses denote the Bellman operator?
Oh no, so P is just the transition function. So you have a Q function on the state action pairs, and you can view P, the transition matrix, as an operator on the Q function as well. So you can basically, it generates another Q function on the next level, next time step. And this P and R together defines an Bellman operator. R is a reward function. All right. So I would like to mention one important open problem. So it's very simple. So we assume that in a linear case, that there is a feature, d-dimensional feature vector that can approximate the optimal Q function with zero approximation error. Okay, so this is a realizable case in the with linear functions. Then can we find linear optimal policy with polynomial number samples? Remember, our lower bound only holds for the feature phi that can only approximately represent the Q star function. So there are some known results that in the deterministic system, there is a polynomial upper bound by Van Rijn 2013. So in order to prove the lower bound, you want to prove it, you need some stochasticity in your Howard instance construction. And there's a very interesting recent work. They show that if the number of actions is exponentially large, okay, then you have an exponential lower bound. So in their construction, they did use some stochasticity in their reward function. Okay, so this is the main open problem, and I know a lot of people have worked on this and failed. So if you can solve it, it's a very big breakthrough. All right, so I would like to move to the next section, and maybe you can ask me more questions after I finish this next section. Okay, so the next section is about the planning horizon problem. Remember this conjecture by Jiang and Agarwal in COLT 2018 that the conjecture there's a polynomial lower bound in terms of planning horizon. Remember the setting is that number of states. So we are working in the tabular setting. So now we can assume the number of states is finite, number of actions is finite, and the total reward is bounded by 1, and they're all non-negative. All the existing upper bound has a polynomial dependency on H, but the lower bound has no dependency on H. Okay, so here I can show you there we have a new algorithm with the following sample complexity. So given target accuracy, say epsilon, then with high probability, we can return epsilon optimal policy using, say, S to the 5th, A to the 1st, and some polylog factor of H divided by epsilon to the 3rd episodes. Okay, so you can see here the dependency on S, A, and epsilon, they are not optimal at all, and they are actually worse than the existing results. Okay, but what we want to highlight is that this is the first algorithm with sample complexity that only scales polylog H. And this is the first result of such result in the tabular reinforcement learning literature. And this answers the open problem in this Jiang et al. COLT 2018 open problem. Okay, and this is a negative answer. There is an algorithm that only needs polylog H sample complexity to find an absolute optimal policy. Okay, so here's our result. But I think more importantly, let me describe why you don't need to pay a poly H factor. So why all existing results or previous results all require poly H factor? Because they all use, I would say, local to global analysis. So remember, we have this perturbation bound in the Q function. Remember, basically, if you have a good estimation of the Q function at each level, say epsilon prime, and then you use the policy induced by your estimation, then you have a near out policy, but you have an H factor blow up. Okay. So in order to find an epsilon optimal policy, you need to set this epsilon prime to be epsilon over H. And for that, your estimation error will need to scale with epsilon over H. That's why you need a poly H sample complexity. Okay. This is a high level reason why existing results require poly H sample complexity. However, this is really local to global analysis because you have a local perturbation bound on each level, small h. Then you transform it into a global policy guarantee. Okay. So instead, we can consider a more global approach instead of going through from this local estimation to the global policy. So the main idea is the following. I think for stats department, you're very familiar with epsilon net kind of arguments, and then you take union bound over epsilon net. You have only log dependency on the size of the epsilon net. So this is our hello idea. So we build an epsilon net for all possible open policies. So how do we build these policies? So we discretize the transition and the reward. Okay. For every state actions next state tuples, say SA S prime, we discretize our transition, all possible transition matrix with epsilon accuracy, also for the reward as well. Then we can prove this perturbation lemma. So suppose I have an approximate version of the true transition and reward function. Say we have a p hat and r hat. And they will induce optimal policy, which is optimal on this p hat and r hat. Okay, so this pi hat is the optimal policy for this instance, p hat and r hat. And let's consider the real instance, which is p and r, whose optimal policy that's known as pi star. Okay, and the expected total reward of pi hat I'll denote as v pi hat. And the expected total reward or the value function of pi star, I'll denote as v pi star. So these are the expected total reward on the true instance, the p of p and r. Okay, so we can prove this perturbation bound that if your epsilon accurate in terms of transition and the reward, then they will induce an policy which has 8h as epsilon close to the suboptimal as for the pi star on the true instance. Okay. So here you still need to pay an h factor here. However, if we count the number of possible policies or epsilon net for the policies, it only appear in like in here. So basically, we can build an epsilon to over 8hs net and an epsilon over 8hs net for the reward and for the transition function. So this epsilon net has this number of size. Okay. Well, the exponent have an s squared a, but here there's no dependency. But here is only a logarithm dependency inside the bracket, right? So if you take log of this number, you have only logarithm dependency on h. Okay. So this is a high-level idea why you only need to pay logarithmically complexity for finding the an epsilon optimal policy. Basically, the number of optimal policy scales say h to the square of s squared a, but in the exponent there's no dependency on h. So if you take the log, there's no point dependency on H. Okay. So after we build this epsilon net for the open policy, we just try to, we have some algorithm to evaluate all of them. And then you take a union bound over the epsilon net, you have polynomial dependency on the planning horizon H. Okay. So here, let me again list some one open problem. So these are the previous results up to 2019. And this is the result I described in the previous slide. We have a huge number of dependency on S and A or epsilon to the third. More recently, we have a new improved algorithm. We can improve to this number, this bound, which is SA or epsilon square plus S square A or epsilon. Okay, so this is the best bound to date. But compare with the, again, also it does not depend polynomially with H. But compare with the lower bound, which again is a contextual bandits lower bound is SA or epsilon square. So there's only one difference now, is S square A or epsilon. Okay, so the open problem or the conjecture is that we believe there is an SA or epsilon square upper bound. Okay, the second term is in fact not necessary. Why this problem is very important? If you can prove this conjecture, you can basically claim that reinforcement learning is just as easy as contextual bandits. Although reinforcement learning is an additional transition matrix, you have an additional planning horizon, but they don't matter by much. Okay, they don't matter much. This, in terms of sample complexity, you still only need to pay SA or epsilon square, which matches the lower bound of a much simpler problem, contextual bandits. So if you can prove this, is a very big breakthrough as well. All right, so let me summarize. Today I talk about two aspects about reinforcement learning. First, on reinforcement learning with a large state space. We proved exponential lower bounds for Q-learning and policy-based learning. And it also talked about some existing polynomial sample complexity bounds. They all require some model or completeness assumptions. And the open problem here is that whether you can prove, say, lower bound or an upper bound for linear Q star with 0 approximation error. And for reinforcement learning with long planning horizon, I show you that logarithm dependency on the planning horizon suffices for the tabular setting. And the open problem here is that whether you can have a new algorithm which only scale with SA or epsilon square sample complexity. In that, you can show that reinforcement learning is basically as easy as contextual bandits. OK, so I would like to stop here and take more questions.
Okay, thanks, Simon. And I think actually there was a question. Yes, I think Sam was asking that to use the union bound here, are you creating an epsilon net over your policy at a particular state or over a set of states?
Oh, this union bound is defined over all states. So yeah, so basically for all state action as prime, as A as prime, we build, we have like our transition function on the epsilon net is approximate the true transition function with epsilon arrow, and also for the reward. And if we, it's for all SA as prime. So yeah, it's basically for all state action and next state tuples.
Okay. So yeah, actually, I also have a follow-up question just on that. So when you think when you are trying to pick a epsilon net, so it's a so should I think about it as like a function p hat, and then it's kind of a it contains this epsilon approximation to all, like basically I need to get this uniform bounds, right? I need to get this uniform. I took a super S prime S and A, right?
Yes, exactly.
I want to construct this p hat that has this uniform bound.
Right.
So the key is trying to show, but I kind of feel that you probably need some smoothness assumptions on that, right? Or do you don't need?
Well, I mean, it's a probability matrix. So the sum of them is 1. So itself has some regularity condition. This is a probability matrix. Yeah, and if you write out the value function, is the transition function times the reward that give you the value function. So, and reward function we assume is bounded. So itself already has some regularity function built in.
I see. Yeah, now I see why the the boundedness of a reward function is quite important here.
Yeah, of course. Yeah.
Yeah. Okay. Other questions? And actually, I just one quick question. I think that was in the pretty previous in your slide that
Yeah.
I think just give me a second. I think actually not. I think it's probably in the page 13. I think in the page 30. I think you probably also It's just very quick. I think. Yeah, I think here when you are trying to say that if the agent has this blah blah blah, I think all these bounds are actually you say for all H, but I think you also have the super over S and A, right?
Yeah, for super and SA.
Okay.
It's a little bit tricky because sometimes a state, suppose you cannot reach it by, for any policy, you cannot reach it with some lower bounding probability. You cannot estimate well, but if you cannot reach it with some lower bounding probability, you can actually ignore it. So there's some tricky part here, but basically at high level, if you have good estimation of all state action pairs, then you have this perturbation lemma.
I see, because actually in that case, I think in a sense we probably only need something more like instead because L infinity could be too strong, but we probably need something that's DP, right? Like integrating over the underlying major. So actually
like basically over all the states that can reach it with a epsilon lower bounded probability, you have this bound, then you can have this perturbation number. Right, that's enough. Yeah.
I see. Yes. Okay, other questions? Okay, I think here's another questions. To get the SA divided by epsilon square bound, do you use a similar epsilon net argument or different technique?
Oh, thanks for asking. So for our very recent result, we use a more classical algorithm. It's upper confidence bound kind of algorithm. It's similar to the previous algorithms, but we use a new upper confidence bound and some new analysis there. So it's not based on epsilon net. Yeah, so actually on November 25th, I'm giving a talk there's a seminar called Reinforcement Learning online seminar. I'll talk about this result. So if you're interested, you can attend. Yeah, so basically it's not it's a different approach. It's a more classical approach, like UCB based approach.
Other questions? And just one small question about like at the end when you are trying, usually it's really impressive, smart idea about using the epsilon net. But I want in this case you have to pick this epsilon divided by A times HS, right?
Yeah.
So this implies the case is if the state space is large, this net is also something that the size of the net will also be something that's quite like, because you have to pick a pretty fine net, right? If S is also large in this case.
Yeah. So here we still consider a tabular setting, which allows your some comment depends on the number of states. So if you want a large state space, I think still doable. I think there's some recent work. Suppose you represent your transition function as in terms of some linear function. You can build a epsilon net or the feature space. Then you can still use the similar ideas there. Yeah, it depends on your assumption.
I see. So I will so in a sense, if it's both large H and large S, then that's going to be a pretty difficult question, right?
Yeah, I think all existing. Okay, for large H, we can have a log H bound, and for large S, I don't think any work has like log dependency on H. Yeah, so that's a very good open question as well. Right. Whether in those like linear function approximation settings, say your reward and transition function is a linear function, and whether you can have a bound that scales only logarithmically with planning horizon H.
I see. But just out of curious, I think empirically, I think they have some method that works well even in the large H, right? Like
I mean, empirically, those deep learning based, they are not too concerned with the long planning horizon. Well, they're like in terms of algorithmic design, you need to add some tricks to to gather reward in the long horizon. And I mean, they do pay a lot of sample complexity, but eventually they can solve it pretty well. I don't think it will fundamentally scales. I don't think it fundamentally scales with like polynomial usage, even for those modern, modern applications.
I see. Yeah. Okay. Okay. Other questions for Simon? Okay. I think if no other question, then thanks Simon again. And yes, it's very insightful talk. I enjoy a lot.
Thank you.
Thanks. Thank you. And have a nice weekend.